Namaskaram. In last class, we have seen that what is a vector valued function and its geometric representation. Okay, today we start with domain of a vector valued function. That is, the domain of a vector valued function r of t is the set of allowable values for t. For example, consider r of t equal to log ti plus t square j, and also given that 1 less than t less than 5. So in this case, domain of this vector value function is the open interval 1 to 5. Okay, because it is given. Consider consider another case. Suppose only function is given. That means domain is not given. We have only function. Then we can define another technical term that is called natural domain of a given function. Natural domain of a vector valued function r of t. So this is the formal definition of natural domain of r of t. If r of t equal to x of t I plus y of t j plus z of t k, here x, y and z are the component functions of r of t, then the natural domain of r of t is defined as the intersection of the natural domain of the component functions. So we have to find the natural domains of these component functions. So here natural domain of component functions means set of all values of t such that these component functions exist corresponding to each component functions. Okay, then we have to take the intersection of all that components. That is the natural domain of given vector valued function. Okay, for example, we consider our previous example r of t equal to log ti plus t square j. Here domain is not given, so we have to find the natural domain of this vector valued function. How to find? So first we have to find the natural domains of these component functions. Okay, here the component functions are x of t equal to log t and y of t equal to t square. In this case, our z value is throughout 0. That means z of t equal to 0. So no need to consider z value. So what are the natural domains of these two functions? And we know that the log function exists only when the argument is positive. That means the natural domain of this first component function is t is greater than 0. That means the interval 0 infinity, isn't it? And similarly, what is the natural domain of this component function y of t equal to t square? We know that this function t square exists for all the values of t. You got it? So the natural domain of this component function is minus infinity to plus infinity. So our aim is to find the natural domain of this function, this vector valued function. So how to find? You take the intersection. So what is the intersection of these two? The one is 0 to infinity, other is minus infinity to plus infinity. Yes, it is clear that the intersection is 0 to infinity. Okay, that means this is our line. This is our set of all real numbers. Then for log t, its natural domain is like this. It is from 0 to infinity. In the case of t square, its natural domain is entire real numbers. So the common part is this one, 0 to infinity. So this intersection is nothing. Intersection is 0 infinity. The open interval is 0 infinity. Okay. So this is the natural domain of this function. Clear? Okay, consider one example. Find the natural domain of r of t equal to log argument is modulus of t minus 1 I plus e raised to t j plus square root of t k. Okay, so we have to find the natural domain of this function because domain is not given. So how to find the natural domain? First we have to find the natural domain of its component functions. Here x of t equal to the log modulus of t minus 1 and y of t equal to e raised to t and z of t equal to square root of t. Okay, so first we consider our x of t, that is log modulus of t minus 1, modulus of t minus 1. And how to find the natural domain of log modulus of t minus 1? And we know that log function exists only when the argument is positive. That means modulus of t minus 1 should be greater than 0. Okay, modulus of something. What is modulus of t minus 1 is positive? Modulus of t minus 1 is positive only when either mod sorry either t minus 1 is positive, right? Either t minus 1 is greater than 0 or t minus 1 is less than 0, isn't it? In both cases, its modulus value is positive. Okay, so t minus 1 is greater than 0 means what? T is greater than 1, or this means t is less than 1. Okay, so this is the natural domain of our first function. Okay, so t is greater than 1 means the so t is less than 1 means what? T is less than 1. So this implies t is less than 1 means the interval of the form minus infinity to open 1. Okay, t is greater than 1 means the interval is of the form 1 infinity. So minus infinity to 1 union 1 to infinity is the natural domain of this function. So entire real numbers except 1. It is the natural domain of our first component. Okay. Next we have to find the natural domain of e raised to t. What about e raised to t? Our function y of t equal to e raised to t. And what about its natural domain? We know that e raised to t is defined for all the values of t, all the real values of t. Okay, so it is clear that its natural domain is set of all real numbers. That is nothing minus infinity to plus infinity. That is minus infinity to plus infinity. So this is the natural domain of this function e raised to t. Similarly, we have to find the natural domain of root t. So we consider square root of t. And what about its domain? We know that square root of function exists only when positive values of t. Clear? So we consider the only real case. If t is negative, this become complex numbers. We consider only real. We consider only real case. Okay. So in the case of real numbers, the square root of t exists only for t is greater than or equal to 0, for non-negative numbers. So the natural domain of square root of t is nothing. It is 0 infinity. Okay. So the natural domain of square root of t as a real valued function, it is 0 to infinity. Okay. Now we have all the natural domains. The first natural domain, the natural domain of x of t is here, y of t is here, and z of t is here. So how to find the natural domain of r of t? You have to take the intersection. So the natural domain of r of t. So in the case of r of t, what is its domain? You have to take the all the intersection. So intersection means intersection of minus infinity to 1 union 1 infinity. This is our first interval intersection. The second one is minus infinity to plus infinity. Again intersection 0 to infinity. So what is its intersection? What about its intersection? Implies what? So if you consider real line, this is our 1. So this is our first part. And what about second part? Entire real number. So again 1 is not there. And intersection 0 to infinity. So 0 is here. So 0 is here. So 1 is not in this domain. Okay, and so its natural domain. So what about the intersection? Its intersection is 0 to 1 except 1 and 1 to infinity. You got it? So the intersection is nothing. It is 0 to 1 union 1 to infinity. So this is the natural domain of this function. This is nothing. It is the intersection of these three domains. It is clear from this graphical representation. You draw a real line and you mark all these intervals. This is entire real number except 1. This is entire real number. Its intersection is again this one. You got it? And intersection of these two. Intersection of these two is 0 to 1 except 1, then 1 to infinity. That is the natural domain. Okay. That's it. So the natural domain of R of t is close to 0, open 1, union, open 1 infinity. Okay. Next, we have to introduce the concept limit of a vector valued function. Actually, the term limit is not mentioned in the syllabus. But for understanding the concept of derivative, we have to study the limit of a vector valued function. Okay. So let's start with the limit. I think all of you familiar with this notation for a real valued function. That means, what about limit from t tends to a, f of t equal to L? Here f of t is a real valued function like t square or sine t, like that. Okay, L is a real number. What is the meaning of this notation? This means this is our a. This means whenever t tends to a, either through left side or right side, the quantity f of t, suppose this is the value L, this height is L. Okay, so this means whenever t tends to a through left or right, our f of t is tending to this height. Okay, that's a concept. Whenever t tends to a, f of t tends to this height. Similarly, what is the meaning of this notation? Almost the same idea, but here only the difference is r of t and L are vectors. Okay, so this means whenever t tends to a, corresponding to every t, in this case corresponding to every t, f of t is a number, real number. That's why we plot like this. Okay, corresponding to every t, f of t is a number. Here corresponding to every t, r of t is a vector. Okay, so whenever t equal to 0, it may be a vector like this. Whenever t equal to 0.1, it may be a vector like this. Whenever t is next value, vector may be like this. So its totality is curve is like this. The curve is the endpoint of these vectors. That's the idea of vector valued function. Okay, so they are all vectors. L is also vector. So this means whenever t tends to a, the r of t is, the vectors of r of t is tending to the vector L. So what do you mean by that? Its meaning is like this. It means like this. The vector r of t approaches the vector L in both magnitude and direction when t approaches to a. That is the idea of this notation. You got it? So I will show you a geometry of this notation. Okay, this is the geometrical representation of this concept. It is clear that corresponding to every t, r of t is a vector. Okay, that's why. Okay, so suppose this is our r of t. Maybe this is corresponding to some value t naught, and when t equal to t1, it may be this vector. You got it? So this vector is nothing. Let it be r of t naught. This is r of t1, etc. Like that. Okay, so this is our given vector L. So this is our given vector L. Okay, so whenever t tending to a, our r of t vectors are tending to this vector in both magnitude and direction. Okay, in this figure it is clear that the r of t is tending to this vector L whenever t tending to a. Okay, so this is the idea of the limit. So next we have to formulate the mathematical definition which is equivalent to this concept. Okay, so how to formulate? So we consider another figure. So here this is our L, and suppose this vector is r of t. So our aim is to define this concept mathematically. That means r of t should converge to L. Whenever r of t converges to L, naturally this distance, the distance between end of these two vectors should tend to 0. Okay, that's idea. So how to find this distance. We know that vector subtraction. Okay, this is our r of t. This is the vectoral. Then how to find r of t minus l? Okay, I already explained how to find r of t minus l. Actually, the actual method is you extend this vector, this vector like this. So this is our minus l. Then we complete the parallelogram because using vector addition, r of t plus minus l. Okay, next we consider r of t plus minus l. So to find that, we complete the parallelogram. Then this is the, we shift this minus l on this end. Okay, that's idea. So this is again minus l. We shift this minus l end of this vector. So like this, then this is the vector. So this is actually this is the vector r of t minus l. You got it? Almost like this. Almost like this. Yes. So almost this is like this. This is the vector r of t minus l. If you shift this vector, 1 second, almost like this. Okay. If you shift this vector at the endpoint of this vector, then they are parallel because this is a parallelogram. Again, this is a parallelogram. That's the idea. Okay. So actually r of t minus l is a vector. So it is always starting from origin. If you shift this vector parallelly to this point, then it is like this. Okay. So our aim is to find the distance between these two. How to find the distance? The length of the distance between these two tip is same as the magnitude of this vector. Okay, so this distance is nothing, exactly modulus of r of t minus l. Okay, so the mathematical definition of this concept is limit t tending to a modulus of r of t minus l equal to 0. So this limit is tending to 0. This limit is 0 means automatically this vector r of t is very very close to l. That's the idea. Okay. So this is the mathematical definition of the concept limit of a vector valued function. If r of t is a vector valued function, then limit t tends to a r of t equal to l if and only if limit t tending to a modulus of r of t minus l equal to 0. Okay. So this result gives a simple method for evaluating the limit of a vector valued function. It says that if r of t is a if r of t equal to x of t I plus y of t j plus z of t k, and they are the component functions, then limit t tends to a r of t is equal to limit t tends to a x of t I plus limit t tends to a y of t j plus limit t tends to a z of t k. Okay, provided the limit of component functions exists. That means you can take the limit of a function as limit of individual component functions. Okay, so this is a very this result is very helpful to evaluating the limit of a vector valued function. For example, we consider find the limit t tends to 0 r of t, where r of t equal to 2 minus t whole cube I plus e raised to t j plus 3 into cos 1 minus t pi k. Okay, here the argument is 1 minus t times pi. Okay. Using this result, you can easily find the limit of this function. Okay. By this result, what is the limit? Limit t tends to 0, r of t equal to limit t tends to 0. What about x of t? Here x of t is 2 minus t whole cube I plus limit t tends to 0. Y of t. Here y of t is e raised to minus t j plus limit t tends to 0 z of t. Here z of t is 3 times cos 1 minus t by k. Okay, what about the limit? Whenever t tends to 0, this quantity become 2 raised to 3, that is 8. So 8i plus e raised to minus t is continuous, so its limit is e raised to 0. So it is 1. So 1j, and this become 3 times. Whenever t tends to 0, this become cos pi. Okay, And what about cos pi? It is minus 1. So there is a minus 3k. So its limit is 8i plus j minus 3k. Okay. So its limiting value is 8i plus j minus 3k. So this is the idea of limit of a vector valued function. Clear? So this is your homework for the session. Okay. Thank you.